session. I tried an hour and then almost went wrong, but I set an alarm. Okay, we will have 2 talks this afternoon on distributed systems topics. The first one is a mix of discussing what we're doing in our group for short, but then a little bit more like a tutorial, because we have come up with some problems we almost every time see in the literature, and we want to make aware of these problems, and so it has to do with more low-level things and performance awareness, so we call our talk performance-aware cloud computing. The next one, that is by Christian Becker, and he will introduce himself, but in between we will have a break. So this is joint work with 2 of my PhD students, Sebastian Boehm and Johannes, who sit there, and you will see them much soon here, because I only do the introduction. So a little bit about the research in our group. It's a small group with 4 PhD students, because that's the reason we give this talk, because we came over these problems during our work. I don't go into these details here because we do that later on. First of all, some common issues about performance in the computing that often go wrong. I hope you are not the ones who write papers where it goes wrong. As usual, everyone inside the room is excluded from these things. If you go out there for coffee, maybe you will count. And then we have some solution approaches, and then at the end, some computing sources. So first of all, the 4 groups. I will go into a little bit more detail about 2 of the groups, 2 of the PhD students, because these are the ones that are not here, and then the other 2, Sebastian Boehm and Johannes, you will see for yourself. First of all, I start with Robin Lichtenthaler. He works on I go now from the higher level to programming language to the more down levels, lower levels. He works on cloud native things, and the basic idea is everybody talks about cloud native, but really what is cloud native? What are the components that make cloud native, and what are the advantages and so on? The basic naive definition would be something cloud native is that if it's dedicated to the cloud and it takes advantage of everything that is in the cloud. And that's a broad scope of infrastructure, characteristics, language, and so on. And the basic idea of this work is to have a multi-dimensional quality model to really get down to the basics, what makes cloud native applications cloud native and what are the advantages. So the idea is, if we think about things like reliability, maintainability, portability, and so on, how are these guaranteed or at least eased by cloud native characteristics? And so the multi-dimensional quality model should explain how quality aspects really in detail architectural characteristics lead to the advantages of cloud native. And then the basic idea is not only to know that, but then to analyze models and see whether they have these characteristics or miss them and so on. And there are 3 main challenges. So the papers are also there. One of them is, the last one is work in progress. We will present in 3 weeks at the SummerSOC in Essence. First of all, how to define cloud native and the characteristics. The second is how to model that in a quality model. And the third then is how can the quality model be practically applied in application architectures. We will have, we give you the slides. Here you find the cloud model, and you will see it doesn't fit, or the quality model, it doesn't fit on a single page, so it makes no sense to show it here. That is the first, at very high level. The second then deals more, and that's Stefan Witzinger, who already has been here, I think last year at the SummerSOC, and he deals with integration testing. And we all know serverless functions are normally more simple than classical software, and a single function is simply more or less unit tests. And so that's very simple, but you may have very complex systems. This is one of the examples of the forthcoming paper. It's a more data-centric thing, but there are also serverless applications that are more like a workflow and so on. And the idea is, if these combinations get more and more complex, how to test the integration testing on this level. And the research questions are, what are suitable models to do that? Are there differences to classical things? For example, you see it here, you have all these things that things concerning data normally are not done in the functions, but they're done through databases or whatever. And then you have transitive relations and dependencies and so on. How to model that and how to get that into a grip on that you can do integration testing in a realistic way. Then we talk about coverage criteria, how to measure them based on the classical ones from testing. And then what's the most important part is we want to do that by hand mostly, but you want to create test cases automatically, do also mutation tests and so on. And then the question is, what are the test cases that are most efficient to get a good view of what may happen in such an application? This is one of the simple models of one lambda function, but you have to take into account. I won't go into the details because I can also share this as a preprint. This is the last paper which will also be presented at SummerSOC in 3 weeks. So that's the both ones are from models to languages, and then we have 2 more. One is the work of Johannes and the other of Sebastian Boehm. The one from Johannes the basic idea is to have a simulation framework where you, before you go into the cloud, you can check whether or not your service system or service function will perform and how will it perform. And so you have the problem, on the one hand you have a development environment, on the other hand you have a maybe costly cloud environment. And so the developed environment is something different from the production environment and so on, or test environment. So we have 2 different, maybe visualized environments. And the basic idea is how to adjust the checks on the development environment in a way that the results are meaningful for the cloud. So you try to go not to the cloud before getting the first grasp of whether it performs or not. So you run your cloud function various resource settings to simulate expected behavior on a function as a service platform. And then how we can develop support with it. Yeah, Guido.
To simulate expected behavior or to check expected behavior?
Simulate.
Oh, okay.
To get some kind of
feeling
how it goes, and then that's the basic. And that was the first. That was the main project where these things we talk about, performance awareness, these details often are overlooked or not documented, come from. And the last one then, as not the least, is to work on a universal platform where all these different algorithms, we do not work on the algorithms themselves, for Internet of Service, IoT platforms, Internet of Things platforms with quality of service requirements can be mapped. And the basic idea is to have a workbench where different algorithms simply can check by putting them in, but the entire infrastructure is there. And Sebastian works on such a lightweight platform for cloud edge orchestration. The universal we will see about universal is always hard, right? So, and this is the other one where this work comes from. So that's the background. Now to the original topic. When you look at a lot of papers, what you see normally, performance surely you all know has to do with resource utilization, latency, costs, and so on. But when you look at a lot of experiments, or the documented in apostrophes experiments, you miss a lot of important information which make it easier to get a grasp whether this result is really meaningful for you or not. So configuration of machines, which kind of processors, what is about multi-threading, and all these things are normally not well documented, which is a shame for a scientific experiment and its documentation. So that was the reason I said nobody here in the room is meant for that. And there are 4 common issues we have. The first is the experiments are not self-documented, and so it's hard to reproduce. The second is if you have multi-core environments, and the impact of multi-core environments, multi-threading and execution is often neglected, and you get surprising results. And if you look a little bit closer in the environments, you find reasons, but normally they are neglected. The third one is if you work with open source software, resource issues are often not discussed at all or not in detail. And the fourth one that's more to do with the IoT. If you think about service level agreements, a lot of experiments do not consider things like reliability and things like that, which are very important. And so our idea is for this talk, we want for everyone who has who works in this field or wants to start in this field, you shouldn't get blindsided by overlooking these blind spots. And these are the 4 blind spots in short you've seen before. And now we will discuss first of all these blind spots, and then we have some issues how to solve these things. And now I hand over to Johannes, who will discuss the first 2 or 3 of them.
This is a general problem in computer science, right?
Yeah, sure.
Absolutely.
It's like naming.
Yes.
It's a hard thing, and often there is no reward for a good documentation in the scientific community. One welcome from my side. I'm Johannes, as Guido already mentioned. The first blind spot, reproducible documentation. So I performed a structured literature review on fast performance experiments and read around about 60 to 70 papers. And most of them were hardly interpretable at the beginning. So I had to make assumptions, what have the others done to interpret results. And when looking at secondary studies, which are, most of them are structured literature reviews, this is to some extent confirmed. So a paper from 2018 in the fast domain, where 3 out of 26 experiments are reproducible based on the documentation and the open source links. Another publication from 2013, where a majority, not further specified, also not really precise, but majority of 122 papers not reproducible based on the author's investigations. And what is interesting is the third one and the fourth one. The third one is looking at data projects and if researchers publish raw data. And for example, that's one of the solutions to this issue. ACM, for example, attaches badges to papers and projects. When you submit raw data, when you submit all the analysis that others can reproduce, can look in detail. And that is one solution idea. The fourth paper here, where around about 1/3 of the experiments use proprietary components in Sebastian's research domain. The problem here is that they are closed source to some extent. So you have no access to the platforms, to the algorithms. You have also to do a lot of assumptions, to reproduce, redo stuff. And that's really a shame for the scientific community that this is neglected a lot. Upcoming is currently in the US. There is a reproducibility group. A lot of people are trying to get more standardized processes. Zenodo, I assume a lot of you know Zenodo, a platform where you can upload research data, then it's so to say a final set. You get a document object identifier, and it's not changeable anymore. And what we come up with in one publication for my research prototype was in the fast domain, guidelines for performing experiments. And there are some really obvious things, but no one does this. So for example, physical machine configuration. What is the underlying physical machine, so the CPU model, the operating system, etc. is documented in 1 or 2 other papers within this set of 60 to 70 research papers I mentioned. The other thing is virtual machine container identification, which is important when talking about multi-tenancy. The next thing in the fast domain is configuring the resources of a cloud function is done by the memory setting, and other resources are scaled proportionally to the memory setting. Programming language, of course, is important when comparing, for example, JavaScript and Java, in implementing the same functionality. What is well documented is the experiment time, duration, and the workload, where often there is a doubt is the data measurement procedure. So do I look at the server execution time, server processing time, or the client perceived performance? And what leads us to the next issue is function application characteristics, especially multi-threading. And I really like multi-threading, but more in a second. What we, when we assess the literature in a structured way, these 3 aspects were most important for a proper data evaluation. So understanding or doing effort to get the physical machine configuration. Runtime programming language is often neglected. I'm not sure why. And the data measurement procedure is also really important. Where do I start my measuring and where does it stop? So guidelines, or we call it Guido lines, or
Someone already noticed.
oh, that was the wrong. Not my pointer, but a nice one. The second blind spot, multi-core environment, and that was really, really interesting. We start with a misinterpretation. The situation in the fast domain is CPU and other resources are scaled based on the selected memory setting. And what is really interesting, that no experiment, despite one where they say that multi-threading is not interesting for fast, no one considers multi-threaded functions, so implemented in a multi-threaded way. When we look at experiments in the literature and the number of papers which include graphics like these are more than 10, we see on the primary y-axis the function duration in milliseconds. Yep. On the secondary axis the price, and on the x-axis the memory setting. And as already said, when I double my memory setting, I double my assigned CPU resources. And what they face in their experiments and publications, they face that, or they experience that the curve flattens out and stays constant, and the price increases. Obviously, a cloud provider, when doubling resources, I also have to pay twice the price for the same amount of time. And in a lot of publications, some do not write about this effect, and others wrote that they wonder why they face this plateau in execution time and the rapid increase in cost. And the explanation is quite simple when looking at the documentation, where AWS, for example, states that 1796 megabytes are equivalent to a single core. And when increasing memory size beyond this limit, or beyond this, this value, you get more than one core assigned, where a single-threaded function does not profit from a resource increase. I think that should be also understandable by undergraduate students. An attempted explanation. So, short comic, there's a problem, let's use multi-threading. Not sure. So Sebastian and I lecture a course on concurrency topics in Java, where we start with volatile, cache synchronization, etc. And the students perform quite well after a semester, but at the beginning, where we talk about synchronize, wait, notify, that's really hard and very interesting to lecture every year. Attempted explanation why researchers do not consider multi-threaded function. So from lecturing this course 4 times, I know this is inherently complex, hard to track over time, and for a good reason often neglected, since this micro-optimization is maybe not worth the overhead or the problems I get when refactoring code, extending my solution, etc. Computer science education, we have a new shareholder for machine, so he does operating system courses and embedded stuff. And in his inaugural lecture, he also claimed that our computer science education is single-threaded per default to some extent for the programming courses. And for example, middleware frameworks like Spring Boot hide multi-threading. So when I use it as a developer, I get a new request and a new thread handles this request. Another attempted explanation is that in other use cases, FAS is very specific. I have a single functionality and I try to fully utilize my machine with this single functionality. In other use cases like platform as a service, where I deploy a whole function, a whole application, not solely a function, I may have a lot of other or various functions running in parallel where they are influence each other. And I have a noisy environment to measure specific effects. Let's use multi-threading. The third blind spot, open source research. So open source machine configurations. In literature, a lot of feature comparison of open source tools and cloud platforms exist. But the open source tools use most often the pre-configured defaults of the tools. Whereas in the cloud, I have to specify which virtual machine do I want to use. Is it A1 to A10 or B or C or an ARM processor or a Windows operating system? So I have to specify my machine. I know the number of CPUs, the number of RAM. In open source software, this is more or less neglected. Therefore, when looking at data, no fair comparison performance-wise when comparing cloud and on-premise hosted solutions. And some authors still claim that they assume, and that's a direct quote, assume the cost of executing a function in the private cloud to be 0. I think we all should do on-prem deployments. They cost nothing. That's really nice. So this is obviously still not true: procurement, maintenance, operating, etc. What is also interesting in open source research, in the FAS domain, but also in the cloud edge stuff, that Kubernetes is nowadays often used as a higher level of abstraction and a foundation for open source tools. And the next 2-3 slides, I want to stress this aspect. Kubernetes is used as a high level of abstraction. And we performed an experiment on Kubernetes on an open source FAS platform. And the deployment was made on a single node to avoid the clustering side effect. And the diagram is as follows. On the y-axis, the execution time in milliseconds. On the x-axis, the number of concurrent users on my single node. And the pods which were used to deploy the functions use the open source default from Kubernetes, or the default from Kubernetes, the resource configuration. What we see here is that we have a massive increase in response time from a single user until 20 users in parallel. Without resource limitations, not surprising. What we see is that pods compete for the resources when they're running in parallel, and they face a performance degradation, which is not visible in the cloud. So there is a really nice publication from 2020 from the guys from Spain, and they talk about noisy neighbor problems in public cloud fast platforms, and they are not present at all. What we did, specific explanation, this is so to say a primer. What we did to make environments comparable, we have an abstract measure, call it for now G-flops. And we show in the second solution how we can use this, but for this solution, pitch here, take it as given that on my local, that are the black dots, again, execution time, and the resource configuration, the black dots are executed on OpenFast on our local machine, and the orange and green dots are executed on AWS Lambda. And the orange ones are executed on 2.5 gigahertz machines, and the green dots on 3 gigahertz machines. What is interesting, they cost the same. So AWS writes a 15% increased bill for getting the same service, so to say. When you are lucky and get a 3 gigahertz machine, you buy less. Also a nice side effect. The vertical lines here are the one CPU equivalents, and they are important when interpreting such diagrams. As we know, multi-threading makes only a difference when I have a multi-threaded function. So for single-threaded functions, I can go until the boundary and stop increasing resources. Or I want to burn money. Problems here are for clean experiments are hardware heterogeneity on public cloud platforms. AWS Lambda uses a bunch of machines to execute these functions, and the one CPU equivalent, as already said, is different. So our solution approach so this was for a single function, a single pod on our local machine, and then we performed another experiment. So the orange dots are the execution for the single user from the slide before, and the black dots are 5 concurrent users executed for 10 times the experiment. And what we see here, we have a slight increase, but we perform a lot better than using the open source defaults. What is especially interesting are the pods or the dots here. So they face -1 execution time. Also nice for a function. On the x-axis is G-flops again. So abstract resource value we use, and the pods which are deployed here are pending pods, starting from 74 G-flops configuration onwards. And pending pods means Kubernetes checks in the background how much resources do I have assigned already, and can I assign more resources? So overbook the machine. And when using limits, there is another concept at Kubernetes. When using limits, this is prohibited. So I cannot overbook my machine. The problem is, so I read this last year when writing the paper, the problem is currently at Kubernetes that these pending pods are pending forever. So when I undeploy some of the other pods, these pending pods are not scheduled automatically. And then I'm kind of in time for my part and hand over to Sebastian.
So thank you so much, Johannes. Also a very warm welcome from my side. I'm Sebastian, and it's a pleasure for me today to present the fourth blind spot today on real-world conditions and reliability requirements. And I would like to do that on my research field, which is, as already introduced by Guido at the beginning of this talk, the context, the research field of cloud edge orchestration. So what you're usually doing in cloud edge orchestration, we have a particular set of applications with some quality of service requirements, for example, the maximum application response time for an end user requesting a device. And we have some applications or algorithms available. So for example, service placement and offloading and scaling are the most frequent algorithms. And the task is basically to deploy the applications, the quality of service requirements on a given infrastructure. So in this case, we have the cloud layer and the edge layer, for example, and by placing a particular application either in cloud or in edge, we have a different response time, right? Because the edge layer usually is in close geographical proximity to the end user. But this also introduces some challenges, of course. So we have a heterogeneous and resource constrained environments. So usually cloud nodes and edge nodes are different in their machine specification, and usually cloud edge orchestration are denoted by an unstable environment and usually faced by volatile network conditions. That means the network conditions are varying over time. And this makes it necessary to implement a proper monitoring of resources and especially network conditions. Which leads us to our next slide, so the neglected real-world conditions. So this table is obtained from a study we performed in 2022, and most frequent are the static resource management, respectively the static network measurement of resources. So for the resources, it's not the worst, I would say, because in the worst case, you're just underutilize your edge nodes because you're assigning all the applications in a static way, which means a node, for example, has 4 virtual CPUs and my application needs 2. 2 nodes are remaining, and if the application is not using all the resources, I have underutilization, but I can ensure that my application is not running out of resources. But for the network metrics, it is quite important to go for the real-time solution because network conditions are varying over time. So we will see that in a minute. So in summary, we have a missing consideration of dynamic resource utilization, and real-time latency and bandwidth, and also energy is not often considered, but this is currently not in the primary scope of our work. So even if we have a dynamic obtainment of real-time resources, for example for CPU or memory resources, there are still some challenges to solve, because most of the approaches for orchestration activities, like for service placement, offloading, or scaling, do not clearly state how they obtain and transform, respectively smooth the data. So you can see this in this chart here. So this is just a sample CPU load curve taken from an edge device or a time. I think we have 15 minutes. And the problem is that there are some solutions that work on a threshold-based decision principle, which means I have a CPU utilization, for example, of 60%, and then I trigger offloading activities, for example. But the question arises, when do we actually exceed the 60%, right? So when is the threshold exceeded? So here we have once the real load, which is the red line, and we have the estimated load, which is basically the blue line, and the blue line is smoothed already based on exponential smoothing with a smoothing factor of 0.8. And as finding in the end that raw data may lead to unwanted operations, right? Because if I consider 60% as exceeded, I already trigger the offloading activity here and not at a later point in time. And also the update interval is necessary to consider, right? Because it is quite important if I measure every 5 seconds or 10 seconds or 15 seconds and so on. And this is especially important for the offloading and scaling activities. So in the end, when should I trigger my offloading activities? For the latency thing, which is quite important, I would say that one of the most important things in Cloud Edge orchestration, because all the activities we're doing it because of improving latency and bandwidth for the end user and for real-time use cases. And the problem is that latency is a manifold term, right? And most papers are stating, for example, the average latency between device A and device B is set to 5 milliseconds. And that gives us some room for interpretation, right? Because which latency is meant? Is it just the end-to-end delay? So the time a particular packet needs to move from A to B, or is it the round-trip delay, which also includes the way back to the sender? And also approximations like the end-to-end delay is just how the round-trip delay is only an approximation, because the packets can take different routes the way to the node and the way back. And there are also different ways to measure. So I think most frequent is the ICMP approach, just measuring the latency via the Internet Control Message Protocol, but this is also possible to use UDP or TCP, and even ping via HTTP, by using the HTTP head command is possible. And what we recommend is an application-aligned monitoring. So if I know that most of my applications are using UDP, for example, it may be worth using UDP as the core latency that I obtain between the set of nodes that I maintain. The following slides underlines the problem I would like to, which I would like to focus here. So this is just a small experiment. So we set 2 machines from Bamberg to Midmere in the Netherlands, and we once measured the latency via ICMP, UDP, TCP, and finally HTTP. And what you can see is, okay, so for ICMP we have around 24. For TCP it's around 25. And for HTTP, yes, please.
So this is after the established connections, after the three-way handshake?
No, the TCP, it's just between synchronize and the acknowledgement. Yeah. Sorry, I should have pointed out this. So this is synchronize and acknowledgement. And for the ping we have the echo request and echo reply. And for UDP, of course, send and receive, because otherwise it's not possible. And for HTTP, you can of course see 60 milliseconds, because it takes the TCP overhead already. So we first need to establish the TCP connection before we can move data between sender and the client. And especially interesting is the UDP, right? Because it's pretty much faster, but it has a higher dispersion, right, over time. So we are starting at around 60, and we go up to 24, and there's a pretty high dispersion over time. And so this emphasizes that it might be a pretty good idea to measure those latency in real time and differentiating by different protocols.
Did you count the number of hops in between the different measures?
Yes, I did that, but I didn't get meaningful results because all the machines were placed into... So the machine and the cloud were placed in the Azure cloud, and I didn't get the right echo replies back because the routers of the Microsoft Azure infrastructure do not reply to echo requests. They are just blocking ICMP traffic, and then you don't get meaningful results back, unfortunately. So
it could be that they change, right? The number of routes in between or hops in between.
Yes, so I stopped counting at 60 hops.
Okay.
Yeah, so it was unfortunately not possible to get the reply back, even if I tried. Okay, so finally some remarks on reliability and requirements. So this is also obtained from the study we performed in 2022. Again, the Cloud Edge orchestration scope, and we determined that high availability and fault tolerance are unfortunately poorly supported, so there was no fault tolerance or high availability in the Cloud Edge orchestration environment. Even they use Kubernetes-based orchestration architecture, because Kubernetes nowadays is the state-of-the-art orchestration tool, which makes it a little bit easier to set up highly available and fault-tolerant environments. And even the container registries were a problem. So there was no replication of the container registry, which might negatively impact the download times, right, for container instances. So for example, if I offload a particular application from the cloud to the edge, I would like to do that pretty fast, right? So a geographical distribution of container registries might be beneficial. So a lot of problems, but there are also a few solutions, of course. So we would like to tackle all these problems, these consistency problems, how to measure things in a unified and configurable framework, which is called Pulsio, Platform for Universal and Lightweight Cloud Edge Orchestration. And what we determined is that the majority of solutions, they are using custom and proprietary components which are not easily accessible. And the symptoms are that most of the inventor, the authors of Cloud Edge orchestration algorithms, they are doing repetitive implementations, right? And this complicates benchmarking and also comparing solution approaches. So the idea would be the implementation of configurable and reusable components. So as you can see here, we have service management, the subcomponent quality of service, and this may be, for example, 8 milliseconds application response time. We have then the resource management, which takes care of all the nodes, the inventory, the infrastructure we would like to maintain, and of course the monitoring. So we need continuous monitoring. And finally, we have the optimization component, which takes care of the placement, for example, but also offloading and scaling might be possible. And this generic architecture is obtained from a meta study performed in 2023 by Costa and all. And our plan is to align our general architecture to this generic Cloud Edge orchestration architecture. Of course, a few problems may arise because the strategies or algorithms for cloud orchestration are quite different and quite complicated. So different approaches like genetic algorithms, machine learning, greedy approaches, exact solutions, and so on. So it is inevitable to decouple the orchestration component. And we are planning to do this via API. So this, you can see this on this slide. So this is just the generic Cloud Edge orchestration architecture, and this is our implementation, and then we are just we are decoupling the optimization via an API. And for all the rest of the nodes we have, so cloud nodes, edge nodes, we would like to align this on a common standard. So the open fork reference architecture, and according to this specification, we are implementing the software, the backplane software for the edge, cloud, and fork nodes. To give you a short example how it should look like. So for example, I would like to run my algorithm, so I'm just creating 2 new edge nodes with particular properties and allocation. Then I can create a logical link between particular nodes, and finally I can assign metrics to this logical link. For example, I would like to measure the TCP bandwidth every 5 minutes by using exponential smoothing with a factor of 0.5 for smoothing the data I get. And then I can use this for my orchestration logic. Again, I have my API. I can read the real-time data I configured beforehand. Then I can execute my orchestration logic. For example, if a particular metric is below a certain threshold, then I can trigger my actions like scaling, calculating deployments, and the according orchestration activity can also be easily performed via the API. So for example, in this case, I scale application A just to E2, and then I adjusting all the routes and configuring my load balancer everything is done by the platform. So finally, a few remarks on reliability considerations. This was also fully covered according to our study. And we would like to provide built-in high availability for all cloud, fog, and edge nodes. So the high availability is completely transparent to the user, so you can see the rough architecture. And here we are planning to deploy on-premises Kubernetes clusters with Kilo Live D, load balancer, and all that stuff. And there's also limited autonomy between a set of edge nodes, for example, because the open fog reference architecture requires that my fog nodes are even operational if the connection to the cloud is completely lost. And of course, we provide a replicated container registry to foster fast orchestration activities like offloading and scaling. So thank you very much. That's everything from my side. And now I would like to hand over to Johannes, who continues with the calibration of testbeds and the proper documentation.
So slicing a presentation in 4 parts was challenging at the beginning, but I think we were good in time calibrating testbeds. Local testbeds. I want to share with you a few things which were kind of interesting when performing experiments at the beginning. We had 2 local machines in our test configuration. H60 is around about 12 years old, and H90 is bought in 2017. So i7 general purpose desktop machines, and the diagrams on the left hand side show G-flops here. So the one or the other may already know what we executed. So we executed linpack. And the x-axis shows CPU quotas. CPU quotas means I use Docker as an execution environment, started a container, and increased in .1 steps the CPU resources assigned to the specific container. And what we got in this first case was a nice linear increase in resources. The more resources enter the container, the more G-flops or the better results I get. On H90 desktop machine, I got this distribution. And then at the beginning, there was, so we all thought, looks strange. And then looked at the Linux kernel documentation and also at Intel sites. And what Intel did with Sandy Bridge, they introduced a custom scaling driver, which is called Intel pstate. And Intel pstate, so when reading in the Linux kernel documentation, for the interested, this is a paper with all the links to the kernel documentation, etc. There are different algorithms to determine the CPU frequency of the machine. And in the standard configuration, these machines are configured with a scaling governor power save to save energy, reduce heat production, etc. For experiments on H90, where I wanted to assign specific resources to a container, this distribution was not usable. So especially for 2.5 CPUs, or also in this middle part, so the whole middle part for this abstract measure G-flops is missing, or is missing from 50 to 150 to assign it in a stable way. What we did is an iterative approach to calibrate our local testbed. And what we did, we changed the scaling driver, we used different BIOS configurations, kernel configurations, and we made to some extent the scaling of resources visible for a developer, user, researcher. And what we did in the end was computing a linear regression model, which when comparing the second and third diagram. So all still executed on this H90 machine. Here again with power save and disable turbo boost. That was one example we performed. And here we changed the scaling governor, so the algorithm determining the CPU frequency from performance to power save. And what this algorithm does is assigning as much resources as it is allowed to. Then we looked in the cloud, and what I wanted to achieve is a simulation framework and making environments comparable. And when looking in the cloud, they have Intel server processors. There we faced also a linear increase when executing linpack for different memory settings. So at AWS, you have the chance to get, for the highest memory configuration, 6 virtual CPUs. So this aspect of using multi-threaded functions, or functions which are good parallelizable, is highly important for your bill at the end of the month, and also for the performance and response time you receive. What we did, again, is computing a linear regression model, and for CPU-intensive function for this class of problems, this equation is super easy, and it works perfectly fine for predicting the execution time locally on a cloud provider platform. The limitation is I have to have a few benchmark points for 1 or 2 memory settings to compute a scalar factor. So the diagram here is I computed quotients AWS divided by the execution time H60 or H90 for different memory settings. And when going when going back here and looking at this equation, I can now equalize both environments and get comparable settings for memory setting, respectively CPU shares, to configure my local container or my function in the cloud. And then I can, based on my machine, compute a scalar factor, and this works perfectly fine until the CPU equivalents come again into play. So on H60, that was the i7 machine from 2011, the one CPU equivalent was already reached at around about 1100 or comparable to 1100 megabytes in AWS. And for H90, this was at 2500 megabytes. And here I see the one CPU equivalent on H60 and here on AWS. And then I see for H60, for example, nearly constant quotients, then decrease. Obviously, the AWS functions profit from the resource increase, whereas H60 for a single-threaded function does not. So this is a short introduction to this test bed configuration and how we use an abstract measure to predict, simulate one environment and make assumptions based on another environment or on the deployment target. So the general solution ideas for this problem test bed configuration was this documentation, or making the scaling visible. That was is one part of the research prototype I implemented the last years. Then there is this idea of an abstract computing measure. So GFlops in our examples, Microsoft Azure, for example, does this already for virtual machine offerings. They have boundaries where, based on their smallest VM configuration, all the others are relatively assessed. And what I find quite beneficial is perform such calibrations up front to get clean and stable experiments. I was once at a performance workshop in Leipzig, and one of the speakers raised his laptop and said, I did my experiments on my laptop and it was super nice, it was loud and hot. I'm not sure how much performance degradation he faced, but not see in the data due to noise. So the results are questionable, to be politely. And limitations for this testbed currently is we focus on CPU performance, as for most of this performance experiments due to the clean and stable results and single isolated functions. For my PhD thesis, I already performed for multiple functions, also simulation. This works also fine. Short summary on our 4 blind spots and the 2 ideas. So the documentation, multi-core environments, open source, resource awareness. So try to question the default configuration, and in the edge environments, real-world conditions and reliability requirements, Sebastian's procedure architecture, and my calibration idea in S2. So I'm not sure about the English word, so we spider a bit. So we thought about what could we use, or how can we use our results. Obviously, the most obvious thought is documentation is key. It's challenging, but it's worth it. And I think research communities should come up with guidelines and also with rewards on good documentation. Otherwise, it's questionable if someone goes the extra mile. Multi-threading programming courses in computer science education. I think that's the most interesting part in computer science education. Thinking about why get I race conditions, where are my problems. So that's super interesting. And where this could help, or where this could lead us, is when thinking about multi-core environments where I deploy a single-threaded application onto. I waste resources. And we talk a lot about CO2 budgets, green computing. That's maybe one direction where it might be interesting to look further. Then abstract computing measures like this Azure Compute Unit or our GFLOP measure could support comparability to some extent for different or for related research in the same research domain. And what we force is a standard architecture for assessing or testing different algorithms and strategies for cloud edge orchestration. And I think, so I doubt this, but it's 1 minute before 4, perfectly in time. Thanks a lot for the attention, and also for my 2 co-speakers. I think I can directly introduce the coffee break if there is no important question, otherwise we are not running away.
We have time for questions.
Who is that at the top?
It's the Crete version of Guido.
Oh, 30 years ago. Almost exactly 30 years ago.
Great.
Okay, then I think coffee break.
Wir haben noch drei Besucher dabei. Ja.
Ein bisschen aufgeladen sein, der normalerweise vorlesen. Das Vorhalten, wenn das Ding eingeschmissen ist, Zoom, erkennt er den. Ich habe das so eingestellt, dass das Ding, weil das ist ein bisschen mehr als bei den normalen Slider, weil jetzt nicht immer ganz, kann man so halten, kann man aber auch frei aufbereiten. Das geht auch. Ja, das ist nur das Vorgefühl. Wenn man etwas schneller auf Vorgefühl, dann geht es wenn er nicht mehr aufgeladen wird, sollte es auch dann also, achso, und wir machen
schon gedacht, du bist mein Foto, aber du bist gemein Foto.
Sie machen das mit dem Beamer. Daneben will man sich extra daneben stellen. Ja, genau. So, genau, ja.
Okay, also ein bisschen lächeln und schießen. Ja. Okay, seid ihr bereit?
Ja.
Okay, eins. Nochmal eins.
Ja.
Okay.
Na, fast.